Okay, so today we're going to kind of start our study of analysis of functions using the derivative and the second derivative to analyze functions. So today we're going to talk about finding maximums and minimums, particularly absolute maximums and minimums for a function. So we're going to start this off by sort of repackaging some stuff that we've already talked about. So I'm just going to start off with a little quick picture here. So if I draw a picture that looks something like this, okay, and I label this function f, and I call that function just a function f, okay. So I think we're pretty comfortable at this point right now. We call this right here a local max, and we call this right here a local min. And we learned earlier in the year that when this function is increasing, the derivative, f prime, would be positive. So if f prime is greater than 0, our function is increasing. And if f prime is less than 0, our function is decreasing. Right? And then this idea of local max and min. What do we mean by local? Well, it's maximum right here in a small area, there's a high point. Or its minimum in a small area is a low point. So we know that if f prime changes from positive to negative, we have f has a local max. Okay? And if f prime changes from negative to positive, f has a local min. Okay? Probably should have some commas there. If f prime changes from negative to positive, comma, right? So these ideas we sort of have had some discussions about in the past, right? So this function right here, where this function's increasing, the derivative is positive. Where this function's decreasing, the derivative is negative, and so forth. So we've seen that idea before, right? And then we could also go ahead and bring up concavity here. The idea of concavity. You can see here, I hope, this function's concave down here and concave up here. And once we introduce the idea of concave up and concave down, now the next derivative down the chain comes into play. Because what does it mean to be concave up physically? Well, if you're concave up, if your function is concave up, what's really happening is your function, your derivative, is increasing. Okay? So like right here, this derivative, the derivative of this function would be increasing all through this time. So like if you're looking to the right of this minimum here, this function's increasing, right? Well, it's increasing at an increasing rate. Okay? It's going up, but how much it's going up by each time is going up. Okay? And then to the left side of here, yes, this function is decreasing, the derivative is negative, but the derivative is actually getting bigger. Because it's becoming less negative as we move this way. Okay? So that's what concave up means. So if we were to sort of put the idea of concavity and tie that together, three things are going on. F prime is increasing. Okay? That means F double prime is positive. Okay? And then that also means, I'll draw some arrows this way, that also means that f is concave up. Okay? And all of these arrows sort of, those three ideas are all intertwined. If one of them is true, they're all true. Okay? And similarly, I might as well switch colors here. Similarly, the idea of concave down. So if f prime is decreasing, I missed an A there, that's like saying f double prime is negative, and that's like saying f is concave down. Okay, so, and then all of these ideas are connected. If one of them's true, they're all true. So that's tying a lot of the ideas about the function and the derivative and the second derivative and increasing and decreasing and concave up and down. That's this information here is tying all that together. If you were listening at the beginning of this video, I said we were going to talk about maximums and minimums. So what I'm really interested in now is the biggest a function ever is, or the smallest a function ever is. Now, if you look at this particular function here, I'm going to erase these concavity marks here just so you can see things a little clearer. Okay? This function does have a local max right there, right? But is that the biggest that the function ever is? Is this point right here the tallest or the highest f value that there is, or the highest y value there is? Well, no. I mean, it's higher right here. Okay? This function has a local minimum. Is this minimum the lowest that the function ever is? Or is it the lowest y value ever? Well, no. There's one lower right there. Okay? So this function here doesn't have what we call an absolute max or an absolute min. It just has a local max and a local min. Okay? But what if we did this? What if we looked at this function and we said, what if I only considered this function between here and here? Okay? So I'm now basically saying I'm looking at this function only between these 2 points. I'm going to move this over a little bit. Okay? Between these 2 points. So I'm not concerned about this, and I'm not concerned about that. So the function is essentially going to stop right there. Okay? And when I do this, I'm sort of restricting the domain to this closed interval. Let's call that A, and let's call that B. Okay, so we're restricting the domain to a closed interval like A to B. Okay? Now, let's ask the question again. Is there a biggest value for this function? Is there some place between here and here that it's the highest? Yeah, right there. Okay, I intentionally wanted that just to be a little bit higher than that point right there. Is there a point between here and here that it's absolutely the lowest? And the answer is, yeah, right there. Okay? So if you restrict the domain, if you close it in, you're always going to have a highest point and a lowest point in everywhere, in every single problem, in every single graph. If you restrict the domain down and you say, I'm going to only look between here and here, you're always going to have a high point and a low point. Okay? Now, where does that happen? Well, sometimes it might happen right here at the end. Or sometimes it might happen here at one of the locals. Okay? I mean, the absolute max of this function was here. The absolute min of this function was here. Okay? So, if I was to summarize kind of what we just said here, we would say any function will always have an absolute. By the way, absolute sometimes is referred to as global. Just like local is sometimes referred to relative max. Any function will always have an absolute max and absolute min on a closed interval. A to B. Okay? And in fact, well, I don't want to. I'm gonna change how I word that. Let's say that. I don't like the way I started to say that. Let's say, in fact, they, the max or the min, will always be local or occur at an endpoint. Okay? So let's see if we can kind of make some more sense of this. If I give you a graph, let's just do it. Let's draw another graph here. If I make another graph, okay, how about we do this? We'll go, and then here's my closed interval. Here's A, and here's B. Now, oftentimes we're going to be given values for A and B. Okay, so there's a function there, over there. It seems really far away when I look at it from here. What's the absolute maximum of that function? Well, the absolute maximum happens to be right here at the local max. So this is a local max, but it's also an absolute max. Okay? What's the absolute minimum? Okay, well, here's a local min, right? Okay, well, I mean, technically a local min is when you have just that low point where the derivative changes from negative to positive. But is this local min, is that the smallest y value that the function ever has on this interval? No, over here at A. So even though this is the local min, right there is the absolute min. Okay? That's always going to be the case if we have a closed interval. Okay? So what I'm going to do here is I'm going to erase the board now, and then we're going to outline a process on how we would algebraically find these maximums and minimums, or I should say maxima and minima. That's the plural, when we use the plural of maximum as maxima. So we're gonna learn how to do this algebraically. I mean, this is really nice and easy to do from a graph, but we're gonna learn how to do it algebraically. So let's erase the board, and we'll be right back. It occurred to me as I was getting ready to outline this process for you. There's one piece of terminology that I have not, I don't know that I've taught you yet, and so we want to learn that. So I'm just going to use a picture to teach it to you. Okay. This point right here where you have a local max, right, and this point right here where you have a local min, right? There's a local min, there's a local max. Okay. Let's say that this has an x value of C1 and this one has an x value of C2. Okay. Both of these places, you notice that the derivative has to be changing sign right here, correct? It has to be changing sign right here and right here. In fact, with this particular function, the derivative not only is changing sign at C1, it actually is 0 at C1. And the derivative at C2 is also 0 because the function has a horizontal tangent there. Okay? Because this is a continuous function, we have a horizontal tangent there. The derivative changes sign, so it must pass through 0, right? So these values, the places or the values of x that make f prime equal to 0, or f prime undefined. Okay, now that's not the case here, because we have a continuous derivative here. The values of x that make f prime equal to 0 or f prime undefined, we call these critical points, or critical values. Okay, I really like the term critical values rather than critical points, but almost every calculus book calls them critical points because it's really just the c is the thing that we're talking about, the critical value. We're not talking about an actual point. I mean, when I think of point, I think of coordinate, okay? But we're really just talking about the x value, okay? So critical values are where the derivative, critical points are where the derivative is equal to 0 or undefined, okay? In fact, let me just real quickly show you what it would look like if the derivative were undefined, okay? This function right here, if you remember, this is called a cusp right there. Remember this? Let's say that's x equals 2. In this particular case, we would say f prime of 2 is undefined, right? But that's still a critical point because the function changes from increasing to decreasing. The derivative is undefined. I mean, you still have a local max there, right? So this is still what we would call a critical point, all right? So I forgot we never used that term critical point, at least formally. I may have said it back in September, but I don't remember. Somebody's texting me here. So let me pause and erase the board, and then we'll get back to this idea of how do we find these absolute max and absolute mins algebraically. Okay, so here we are. We're back. So we're going to outline a quick process and do a few examples of how to find the absolute max and min of a function algebraically. And we're talking about on a closed interval a to b. Okay. This process is really simple. It's very simple. It's basically 2, maybe 3 steps, depending on how you put it together. Okay. Your first step is to find the critical points or the critical values. Now, how do you do that? How do you find the critical points algebraically? AKA set f prime equal to 0. Okay, set your derivative equal to 0. Okay, and then solve it, obviously. And then the solutions, x equals c1, c2, etc., those are your critical points or your critical values. Okay, and then step number 2 is, I used to just say f everything. But that, I don't know if that makes enough sense. It might also kind of sound inappropriate. So what do we mean by f everything? Well, basically I mean you f the critical points and you f the endpoints. And the easiest way to do that is to make a chart. So you just have an f of x chart, and you can use a calculator or Desmos to help you with this. Then you put your critical points here, C1, C2, as many of them as there are, and then you put your endpoint, A and B, and then you just F them. And guess what? Because of what we said earlier, remember, the critical points are places of potential local max or local min, right? The only way the derivative is going to change sign is if it either goes through 0 or it's undefined. So critical points are the potential places of local max or local min. And we said earlier that every function on a closed interval is going to have an absolute max and an absolute min. And it's going to occur either at the local or on the endpoints. Okay? So all you have to do is look over here at these y values, and the largest is the absolute max, and the smallest is the absolute min. Okay? It's that simple. Find the critical points, F everything. Okay? I'm going to erase this, and then we'll do an example of it. Hopefully you got a chance to write that down. And then we'll look at maybe 1 or 2 examples of this. Okay, so here's our example. I think this is problem number 123 in the section. Okay, so they give us this function, f of x is x plus sine of x, and they say find the absolute min and max on the interval 0 to 2 pi. Okay? So find the absolute min and the absolute max on the interval 0 to 2 pi. So what's our first step? First step, if you go back, is find the critical points. Find the critical values. And how do we do that? You take f prime and you set it equal to 0. So first, let's find f prime of x. Okay, so now we're derivative masters now. We can do this. That's 1 plus cosine of x, right? And then what do we do with that? We set it equal to 0 and also find out where it's undefined. This particular derivative is defined everywhere, so we don't have to worry about that. Now, if you had something that had a radical in it, or maybe a denominator, then we might have to see where the derivative is also 0 or undefined. Okay, so I'm going to go ahead and algebrate this. I'm going to get -1 is cosine of x. So this looks like x equals pi. Okay? So I've got the critical, there's only one critical point on this interval, 0 to 2 pi. We got x equals pi. So we have the critical point, singular. And what's the next step? F everything. So we're going to make a chart. And I'm going to go 0, because that's the first endpoint. I'm going to go 2 pi, that's the second endpoint. And then I'm going to go pi, because that's my critical point. So I'm going to just take these 3 numbers and F them, okay? Now, here I'm going to show you how I would do this in Desmos. I think I could do these in my head. In fact, let's just knock it out real fast. F of 0 is 0 plus 0. F of 2 pi is 2 pi plus sine of 2 pi, which is sine of 2 pi is 0, so that's 2 pi. And F of pi is pi plus sine of pi, which is pi. Okay? So, the largest one of these is the absolute max. And the smallest one of these is the absolute min. Okay? Now, poor little pi here gets left out, right? I mean, nothing happened there. So what's going on at x equals pi? Okay, well, the derivative was 0 there, so that's probably a local min or a local max. Maybe, not necessarily, because in order for this to be a local min or a local max, the derivative is actually going to have to change sign at x equal pi. Now, in fact, it does, and we'll see here in a second that it does when we look at a graph of this. So I'm going to walk over to the computer. And here we are at the computer, and now I'm in a Desmos window here, and I'm going to say, let's graph f of x equals x plus sine of x, I believe it was, not sine of x, sine of x, okay? And then we were interested in this from 0 to 2 pi, right? So 0 to 2 pi is, if we want to change the window over here, I can actually just go change it right there and say 0, x-axis, 2 pi. Okay, get that out of the way. I don't know if I can move that out of the way. Yep, can. All right. So here we are, right? So let's take a look. Well, here's how I would do what we just did on the table. You have a couple options here. Since I defined this as f in Desmos, I could just be like f of 0. And it's 0. And then I can do f of pi. That's that. And then f of 2 pi. And that's that. Okay? Or you could have actually gone up here and, whoops, didn't want to do that. You could have gone up here and inserted a table right here. But I think it's probably just as easy to just define f and then f the things that you're interested in. Oh, I deleted f of 2 pi, so let's go back and put it in there. Okay? So now you can see, here is our, I'm going to zoom out a little bit. There's f of 2 pi is out here, right? 6.28, so there's the absolute max. There's the absolute min. And then what's going on at x equals pi? 3.14. Ooh. What is going on there? Is that a local max or a local min? No, it doesn't look like it. It's a flat point. So if I go back to the board here, I sort of have to renege on what I said, that this point right here at x equals pi, we said it might be a local max, it might be a local min, but guess what? In this particular case, it's neither, because the derivative must not change sign there. How do I know that from that graph? That graph didn't have a local max or a local min. So how could I verify that algebraically? Well, if I go here and I just think about f prime, and I make a sign chart for f prime. There's f prime, right? Right here. So We know f prime of pi is 0. We algebraically figured that out, right? Well, what if we plugged in a number just to the left of pi into our derivative? What if we plugged in, say, like 3 into the derivative? 1 plus the cosine of 3. Okay? Is that going to be positive or negative? Okay? Well, it's going to be positive because the cosine's only going to be between 1 and negative 1, right? And 3 is almost pi, so it's in the second quadrant. So this number right here is going to be a negative number, but it's not going to be smaller than negative 1. So 1 plus something like negative that's not bigger than negative 1 is going to still be a positive number. So the derivative is going to be positive to the left of pi. And that's actually verified in the picture of the graph because that function that we drew was increasing, okay, before x equals pi. And then on the other side of pi, so how about what's something a little bigger than pi? I don't know, how about 4? 1 plus the cosine of 4, same thing. Derivative is still going to be positive. So the derivative didn't change sign at x equals pi. So that's why that graph at x equals pi looked like this. It was just a locally flat flat pot? It'd be like I'm from Boston, flat pot. No, a locally flat part. So that's that. So here's, just recap the steps here. We found our derivative. We set it equal to 0, found the critical value, and then we effed everything. Okay, and then we just verified what we did on the graph. Now again, you guys could probably use Desmos to help you out with some of the effing here. You know, especially if the functions get a little complex. I mean, I don't want you doing a bunch of that calculating by hand. So there you go. There's your example of finding an absolute min or max algebraically on a closed interval. There's one other thing I want to talk about, so I'm going to erase the board and we'll be right back. Okay, so the last thing I want to mention in this video is, what about an absolute max or a min if we're not talking about a closed interval? Is it possible to have an absolute max or an absolute min if you're talking about not on a closed interval? Like, could you, if I asked you to draw a function right now that has a highest point and that you're not looking at just, you know, between two dots like we were before, could you do that? And I'll bet you, if you thought hard enough about it, you probably could. You could probably draw something that looks like this. Okay? Do you see that has an absolute max? Okay? Absolutely. Ha! It does right here, right? That's an absolute max. Now, does it have an absolute min? No, because if I stick arrows on here, which I guess I should have initially, if I stick arrows on there, that function's domain's negative infinity to infinity. It just goes on forever down, right? But it does have an absolute max or an absolute min. So I want to investigate something like this algebraically and show you what might happen. So I'm going to give this function a rule. I'm going to say this function is negative x minus 1 times x minus 3. Okay? So let's go through this process that we just did a minute ago. Now, in order to take the derivative of this, I don't really want to use the product rule, so I'm actually going to expand this. So that'll be x squared minus 3x minus x is minus 4x plus 3, and then I'll change the sign. So that's negative x squared plus 4x minus 3. Okay? So that's the function just rewritten. We did some algebra 1 there to get that kind of the way we like it. All right, so now let's take the derivative. Let's find that critical value. Okay? So the derivative is going to be, what, negative 2x plus 4, right? And we're going to take that derivative and set it equal to 0. I feel like this marker's running out. Maybe this one's got some more juice to it. Okay? So we're going to say 2x, oh yeah, that's good. 2x plus 4 equals 0. And so, what is that? 2x equals 4 after I divide by the negative, so x equals 2, right? So that's my critical value. Okay, by the way, I mean, I think we could have used our quadratic knowledge to find that critical value. You know that the vertex of a parabola is at x equals negative b over 2a. And that's what Well, it's what we would have gotten if we would have done negative b over 2a right there. In fact, one of the first problems in your homework tonight is to prove why that works by using ax squared plus bx plus c. Use calculus to prove why that vertex formula works. Okay, take the derivative of that and set it equal to 0. See what you get. Okay. All right. So we got x equals 2 is our critical value. So I know this is happening at x equals 2, right? Now, if I make a sign chart for this derivative, all right, and I label that sign chart nicely. Anytime you make a sign chart, you should always label them nicely. Okay? This derivative is positive, negative, right? Positive, negative. You can conclude from this positive, negative that we have a local max at x equals 2. Okay? How can you conclude? Now, this is going to take some thinking and some reasoning. How can you conclude? How can you conclude? I can't say that. That this is the absolute max forever. How can you conclude that? Now think about this for a second. What's the function doing before x equals 2? What's the function doing before x equals 2? It's increasing. According to this, what's the function doing after x equals 2? It's decreasing, right? And it's decreasing forever. So I know that we hit a high point, and then for after that, we were just kept getting smaller and smaller and smaller. So we have a local max at x equals 2, and no more places where the function's going to change from back to increasing, right? We got no more critical points. So at x equals 2 is an absolute max. Okay? So sometimes you have to use some reasoning with your knowledge about the derivative and the increasing and decreasing of the function to make a conclusion that, hey, yeah, that's the absolute max, but or that's the local max, but that's the absolute max too, because after that, the function is just decreasing forever. Okay? And then you can make the similar case that there's no absolute min. This function does not have an absolute min because before 2, the function's going up, and it came from negative infinity, so that's really small. And then after 2, it's going down, and that's really small. So it's never going to be absolutely minimum. It's negative infinity, okay? And we don't say negative infinity is the absolute min. We just say there is no absolute min. So that wraps up this video. This is actually going to be 2 or 3 different videos that I merged together. Do some video magic, but I'm not really that good, so you're probably going to know where I merged. So, yeah, we'll see you.